So in our last video, we did this part of the syllabus. So in today's video, we are going to take the remaining part, which I divided into chemical equation, uses of chemical equation, that is the information given by chemical equations, the relative atomic mass, the relative molecular masses, and then the mole and Avogadro's number, and finally stoichiometry. So that said, let's get straight into it. Okay, so chemical equation is a way of representing a chemical reaction, and a chemical reaction is that anytime a chemical change occurs, that is a chemical reaction. So chemical reaction is another method of telling a chemical change. Chemical reaction is another name of a chemical change. So once there's a chemical change and a new substance is formed, it is a chemical reaction. So you know that there are the substances that were before the change and the substances that come after the change. So those substances that were before the change, they are called the reactants. Okay, those are substances that came together to form the new substances. While these new substances that are formed, they are called the products. So a chemical equation is like this. They write the reactants at the left hand side and the products at the right hand side. So this now forms the whole chemical equation. Now, just basically on the topic of chemical equation, what you ought to learn, what they expect you to know, is how to balance chemical equations. Okay, how to balance chemical equations. That is, the same amount of one substance at the beginning of the chemical equation should be the same amount of that substance at the ending. Remember, we said this earlier in our last video in the law of conservation of mass, that the same amount of matter of that substance in the beginning is the same amount of matter at the ending, because matter can neither be created nor destroyed. So if I have 12 grams of carbon at the beginning, I will still have 12 grams of carbon at the ending. Okay, so at the end, matter is always conserved. Hope you get the point. So there are just few laws that govern the balancing of chemical reactions. So number one is that you don't balance chemical reactions by changing the subscript within the formula, but you change the multiples of these formulas. Okay, what do I mean? If you see a chemical formula like H2O, you don't balance it by changing that 2 to 3 or to 5 to try to balance the masses. No, it is the amount of the whole water molecule, because once you change the numbers within the formula, you are changing the kind of compound. So you change the amount of the compound, which is the multiplier at the side of the compound. Okay, so now the next rule is that compounds like hydrogen, nitrogen, chlorine, oxygen, they are diatomic. So anytime there's a chemical reaction and they are left on their own, try to make them diatomic before using multipliers. Okay, so and also other compounds, if they are not diatomic, you can just represent them by their chemical formula, things like sodium, potassium, copper, iron, and so on. If they are alone, they are not diatomic. Now, radicals remain unchanged before and after the chemical reaction. Radicals are groups of atoms that carry charges. Radicals remain unchanged before and after the chemical reaction. Okay. Now, lastly, you should know that balancing of chemical reactions is by trial and error. But the more you do it, the more you get used to it, and the more you'll be able to play around with numbers to balance chemical reactions. So now let's go. We are going to balance just a few chemical reactions before we move on. Okay, so if you have to balance this chemical equation, that is the combustion of ethane to give carbon dioxide and water. Okay, so I'm writing it out: carbon dioxide and water. Now you can see that there are two carbon atoms on the left, but just one. So I try to balance that by adding 2 there. Now there are 6 and there's 2 here. So if I put 3 there to make the hydrogen to be 6. Okay. But now you can see that oxygen is 4 in this side and then 3 in this side, making a total of 7. Okay. But on this side you can see that there's only 2 atoms of oxygen. So if I put 3.5 there, 3.5 multiplied by 2, that is 7. So we should now balance it, right? Yes. So these ones will also be 7 atoms. but normally you don't leave this 3.5 in the equation. So I multiply everything by 2 to take that out. So I rewrite the chemical equation as this. So that will now be 7. So this will now be 4, and this will be 6. So that's how I have balanced the chemical equation. So now we go over to the uses of chemical equation. That is information given by chemical equations. So you can always get the stoichiometry of a chemical equation. That is the mole ratio, the mass ratio. Like if you have a chemical equation as this, you can get the ratio as this, right? So this is the mole ratio of the chemical equation, and so on. So you can get, so this mole ratio or mass ratio is called the stoichiometry of this equation. Okay, you can always get the stoichiometry from chemical equations. So the second thing you can get from chemical equation is the masses of each compound. Don't worry, we'll soon go into how to calculate relative molecular mass. So you can get the amount, that is the total mass of the substance, from the chemical equation, from the information given by the chemical equation. All right. So the next is, you can, from the chemical equation, you will know the reactants and the products involved, and this is very, very clear. And now if they are gases, you can get their volumes. So if it's 1 mole of a gas, it contains 22.4 decimeter cube of the volume. Okay, so if it is 3 mole, now you see that it is 3 times 22.4 decimeter cube. That will now give you the respective volume, that is if they are gaseous. Okay, so now the next information we can get from a chemical formula is that if you know the amount of the reactants and amount of the product that ought to react, you'll be able to know the one that is in excess. All right, so if it's supposed to be 5:1 and one is now like 6, you know that that one is in excess in this reaction. Okay, now we move over to the last one, which is the states of matter. Mostly in a chemical reaction, you see that they write small letters like S, L, G. That means solid, liquid, gas. Okay, that's used to represent, to tell the state of matter that that compound is, but it's not always given. But if you can give it to give a complete chemical equation. Okay, so now we move over to the information that is not given by a chemical equation. That is, what are chemical equations not used for? Number one is like the physical state. They don't tell you whether the color of the compound. Okay, they don't tell you the color of the compound. They don't tell you whether the compound is rough feeling or is very smooth when you touch it. Okay, so just on the chemical equation you can't get those information. So that's one. Then next is that they don't tell you whether the compound is concentrated. That is the condition of the reaction. They don't tell you whether from the chemical equation, because an information can be given beneath the chemical equation, but just looking at the chemical equation, you will not be able to know whether it was an exothermic reaction, or whether it was concentrated, it was diluted, and so on. And also from a chemical equation, they don't tell you the speed of the reaction. Like, they don't write the speed of the reaction, the time it took for the reaction to be completed. Okay, so now that we are done with the uses for chemical reaction, I'm going to go to the next deal of the table, and I think that is the relative atomic mass, and relative molecular mass. So the relative atomic mass, this is the number of times the average mass of an element is greater than 1/12 the mass of carbon-12 isotope. So get that definition. While the relative molecular mass, this is the sum of the masses of all the elements that are contained in a molecule. Okay, don't worry, you understand this one, we use it for a calculation. Okay, so we are to calculate the relative molecular mass of sodium tetraoxosulfate 6. Okay, sodium tetraoxosulfate 6. So the atomic mass of the sodium is 23. So we multiply that by 2 since it's 2 atoms of sodium. Now that of sulfur is 32. So write that down. That of oxygen is 16. We multiply that by 4 to get the total mass of oxygen in this molecule. So for this we have 46. We bring down that 32. and then finally for all this we have 64. So if we add all of them together, we get the total mass of the molecule, which is 142 grams. So let's go to percentage composition by mass. If you calculate the total mass of a compound and then you compare it to the certain mass of an element in that compound, you can get the percentage of that element in that compound. Hope you guess what I mean. So now from the sodium tetrasulfate 6 that we use in the example of the relative molecular mass, we calculated the whole mass as this. So now the individual mass of sodium is 46. So we divide 46 by the total relative molecular mass. Then from that now we can now have, then multiply by 100. We have the percentage of sodium that is in that compound. So that's what percentage composition by mass is all about. So now that we have said that, let's go straight into the next deal on the table, which is the mole and the Avogadro's number. Okay, generally the mole will give you one definition, but I will give you a simpler one. Okay, so the definition you mostly see is that a mole is the amount of a substance that contains as many elementary entities as there are in 12 grams of carbon 12 isotope. Okay, all right, so I'm going to give you a simpler definition. So a mole is just like group of atoms. Just understand it that way, group of atoms. So a mole is just a group of atoms that come together. So a mole generally contains 6.02 times 10 to the power 23 atoms. So these are the number of atoms that come together to form 1 mole of a compound. And this 6.02 times 10 to the power 23, which is the number of atoms in a mole, is called the Avogadro's number. So here are simple calculations that you can use to calculate a mole that you might see in your Jamb exam. So a mole is calculated by the reactive mass divided by the molar mass. That is, if you know that the molar mass of sodium is 23 grams. Now I now tell you that you have in a sample of 11 gram of sodium, what is the mole? That is, what is the amount of mole present? You can now divide 11, which is the reactive mass or the available mass, by 23, and you have your respective mole. That is the mole of that substance. Okay. Now you can also calculate mole by the number of particles, then divided by the Avogadro's number. Okay, the number of particles divided by the Avogadro's number, which is the number of atoms in a mole. So now move over to stoichiometry. Okay, stoichiometry is very broad. I wonder why they just added it to this topic too. Because if I want to truly treat stoichiometry in this video is going to be very, very long. So I don't add it in this video, so the video won't be too long. But I'm going to make another video to back up this video, just basically on stoichiometry. So do well to subscribe and turn on the notification so that so when I post the video on stoichiometry, you'll be notified. All right. But we are just going to touch the little basics of stoichiometry for this video. Then we go into the past questions that come on this topic. Then we can take a break here. Alright, so stoichiometry is just simply calculations involving mass, involving mole, involving volume from reactions. So you use the information given by the chemical reaction, like we explained earlier, in calculations to predict masses. Like you can be given things like, if this gram of A reacts with this gram of B, what will be the gram of C that is produced? Okay, just like that and like that and like that. So we are going to just take a few questions and then we'll go to the past questions. How many grams of carbon dioxide will be formed from the combustion of 105 grams of ethane? Okay, so this is the balance equation of the reaction like we got earlier. So we are going to check what mass of ethane reacts to form the certain mass of carbon dioxide, then we're able to calculate the question. So here you can see that I'm trying to get the relative molecular mass of ethane, but I multiplied everything by 2 because it is 2 moles of ethane that is in this equation. So when we are done with that calculation, we'll have our total mass as 60 grams of ethane. Okay, so now I multiply that of carbon dioxide by 4 too, since it's 4 mole of carbon dioxide. So I'll use that to calculate the total mass of carbon dioxide that is formed from this 60 gram of ethane. So which that will give me the mass of ethane, the mass of carbon dioxide formed. So this is 176 gram. Okay, so now use the normal mathematics rule, or should I say trick. 60 gram of ethane gave 176 gram of carbon dioxide. Therefore 105 gram will give me x. So if I cross multiply, I'll have 60x is equal to 105 times 176. Then divide both sides by the coefficient of the unknown. So that will give us our final answer. So we'll put that detail in the calculator, and then we have the respective answers: 308 grams. So that's the gram of carbon dioxide that will be formed. Okay, so our first question is from Jamb 1981. The number of atoms in 1 mole of a substance is equal to A. The atomic number, B. The Avogadro's number, C. The gas constant, D. The number of neutrons, E. The number of electrons. So you can see very well that the answer is B, which is the Avogadro's number. Remember we said a mole contains 6.02 times 10 raised to the power 23 particles, and that particles is the Avogadro's number. That is the number of atoms in a mole. So our next question also from Jamb 1981. In an experiment, 5.00 gram of a metal gave 10.59 gram of its chloride. In another experiment, 1.50 gram of the same metal reacted with 1.68 gram of chlorine. The above data illustrates A. The law of conservation of mass, B. The law of definite proportion, C. The law of multiple proportion, D. Gay-Lussac's law, E. Avogadro's law. Okay, so we have been told that 5 gram of X gave 10.59 gram of its chloride. Okay, that is X chloride. Now 1.50 gram of X reacted with 1.68 gram of chlorine. Okay, so normally to form the chloride, X plus chlorine will give X chloride. Okay, so if this, or the first case, was 5 gram and it gave 10.59, okay, 5 gram gave 10.59. So you can see that the remaining mass, that is the mass of chlorine, will be 5.59, all are in gram. Then we say 1.50 gram reacted again with 1.68 gram. Okay, the ratio of chlorine to X in both cases, that's what we are trying to find. So for the first case, we divide the amount of chlorine by that of X. Okay, so you can just put that in the calculator, and what do we have there? We have 1.118 as the ratio, and now in the second case, 1.68 divided by 1.50. So what are we going to have in that case? Okay, so we have 1.12. So now you can see that if I approximate the one in the first case, we can still have 1.12. So you can see that the ratios are the same. The ratio in which chlorine reacted with X, they are the same. So this shows the law of definite proportions. That is, the proportion in which they react is definite, they are the same, is constant. Okay, the law of definite proportion. So that is their indefinite ratios. Okay, So the answer is B. The answer is B. Okay, so our third question is also from Jamb 1981. Wow, so impressive. So many questions from this topic just in 1 year. If 1 mole of aluminium contains 6 times 10 raised to the power 23 atoms of aluminium, how many atoms are contained in 0.9 gram of aluminium? So in 1 mole of aluminium, the mass is 27. That is, the atomic mass is their molar mass. That is the mass of 1 mole of that atom. Okay, so we are just going to use the information given by the equation, and with normal mathematical methods we will be able to calculate it. All right, so we're told that 1 mole, which is 27 gram of aluminium, gave us 6 times 10 raised to the power 23 atoms. Okay, so 0.9 gram of aluminium will give us what? We're just going to use the normal mathematical cross multiplication method. Okay, so let me just simplify it. 27 gram of aluminium gave 6 times 10 raised to the power of 23 atoms. Then 0.9 gram will give me what? Which I say x, then I cross multiply. So we have 27x will be equal to 6 times 10 raised to the power of 23 multiplied by 0.9. So I divide both sides by 27. So the answer is 2 times 10 raised to the power of 22 atoms. Thank you for watching to the end of the video. If you are not yet subscribed, please do, so you won't miss any of my further videos. And please do me a favor by hitting the like button so that more people can see this video, and you can also share with your friends. And don't forget to leave comments on maybe some parts of the video that maybe you're expecting I explain something but I didn't explain it. You can leave questions and I'm sure to answer you by God's grace. And also you can leave suggestions or comments or whatever, and also you can suggest things that I should add in my next video, because I'm going to go straight to topic 3 now, but I'll do the stoichiometry video before topic 3. But you can leave things that you read from topic 3 that bother you. You can leave them in the comment of this video, so that when I'm doing topic 3 I'll take those into consideration too. So topic 3 is a kinetic theory of gases, like all those gas laws like Boyle's law, Charles' law, um, Dalton's law, partial pressure, ideal gas law, general gas law, just all those ones, and the kinetic theory of matter and all that. So you can go and read the topic now. Then drop your comments on this video, or simply drop them to the community post I'll be posting. I'll be posting this week on kinetic theory of gases. So you can just drop all your questions you had when you're reading the topic, and so that I can put those into consideration, and then I'll be able to talk about them. All right, so I think that's all. So see you next time. Bye.